Welcome to this lecture series in real analysis. In this lecture, we'll discuss the notion of the limit of a function at a given accumulation point. We will define everything properly. So, of course, we will need to know about accumulation points. Let me maybe recall the definition. So, you have a subset S of real numbers, non-empty. You say X in R, not necessarily in S, but in R is an accumulation point of S if every deleted neighborhood of X finds a point in S. So is an accumulation point if for every deleted neighborhood of X, deleted neighborhood D of X, D intersection S is non-empty. So S is kind of reaching closer and closer to X. It might not contain X or may contain X, but in some sense it is X is in the purview of S, so to say. Anyway, we discussed this at length. We of course need to know about the epsilon delta definition of continuity. This is a given. And in this lecture, we'll be able to generalize the notion of the limit of a convergent sequence. I hope I don't forget to mention this comment. Okay. Here are some problems for practice. And now let us get started. So first, let us try to at least motivate what are we trying to capture. I'll try to motivate it. I don't know if I'll do a good job. So fix a function from an open interval a comma b to reals. Let's say this is the graph of the function. And now let's look at the real number b. B is not in the domain of the function. That's okay. Still, if you look at points which are nearby B or in a neighborhood of B, but also in the domain of F. So the points which are in a neighborhood of B and also in the domain of F are such points. One such, you take one neighborhood of B, this is one neighborhood of B, and intersect with the domain, you'll get all these things. And if you look at the behavior of the function on this part, it kind of is trying to scream that as you come closer and closer to B, the function becomes closer and closer to this value, whatever that value might be. It is almost like the function wants to take a value at B, but since it is not defined at B, it's not very happy. There is a well-defined value that there is a real number we can associate to the real number B, which somehow is capturing the local behavior of the function around the point B in a certain sense. It's kind of capturing what the function is trying to become at the point B. Okay, and we don't necessarily need to take the boundary of the domain. Let's take a point inside the domain. Let's call this point maybe C. And here also, if you look at a deleted neighborhood of C, which looks like that, and look at the behavior of the function around or in that deleted neighborhood, you'll see that if you look at what happens on the left side, the function is trying to become that, and if you look at the right side, the function is trying to become that. And the left and right sides kind of agree that yes, the value we want to take is same as the value that the function has taken at C. Right? Now you could disturb the function at that point. Let me try to disturb it. I don't know if I'll be able to do it very well. Let me try to disturb it. Let's say at the point C, the function was taking this value. So at this real number, the value that the function takes is that. So up to that point, it behaves like that. Suddenly it jumps, then it comes back and behaves like that. So at the point C again, if you look at the deleted neighborhood, everything about the function is speaking to the function trying to be this value at the point C, but at the point C somehow the function betrays itself. So the notion of the limit captures what happens in a deleted neighborhood and what does that deleted neighborhood say about what the function wants to be, not what the function is. This may not be clear. What I'm saying may sound like garbage. That's okay. It will connect ultimately. Also, we do not want to say anything about what the function does here. There is, in the deleted neighborhood of this point, there are no points from the domain of the function. So the technical way to capture this is that we will talk about the limit of the function f, if at all one can, only at the accumulation points of the domain. This point is not an accumulation point of the domain, while a, b, and everything in between is an accumulation point. So we will be able to talk about the limit of the function there. Before we look at the formal definition and all that, let's see an example where we do not have a limit, where we have a function which we would, to begin with, agree that this function is flailing about a bit too much. So consider the function g, whose graph I cannot fully draw, but let me convey the idea. At 1 it is 1, at half it is -1, and in between it interpolates linearly. At half it is -1, and at 1/4 it is again 1, and it interpolates linearly. At 1/8 it becomes -1 and interpolates linearly, and so on. So it's zigzag, zigzag, but the frequency of the zigzag increases as you come closer and closer to the origin. And now if we look at a deleted neighborhood of the origin and the points which are in the domain of the function, meaning such a thing, here if we look at the behavior of the function, it is just too much zigzaggy. And there is no one specific real number that the function is trying to be. It is betraying every real number. It is just moving about a bit too much. So we would like to say that g does not have a limit at the origin. All right, and so that's basically the rough two motivating examples which roughly motivate the notion of a limit. And now let us look at the formalism. There is much more to say. These two examples don't capture everything, but let's now start with the proper formal stuff. Okay. So let's set it up. We have a function. This be a function. This be given, where S is a subset of the reals. Okay. And let x0 be an accumulation point of the domain. All right. Then we write lim x going to x0 f of x is equal to L. Even before this line, I should have written let L be a real number. Then we write this is statement. This is just a notation. And we read it as limit x going to x0 f of x equals L. That's how we read it. If for all epsilon greater than 0, there exists delta greater than 0, such that whenever we pick a point, first of all, in the domain of the function, and in the delta deleted neighborhood of x0, we get that this is the case. So forget about what the function does at x0. x0 might not even be in the domain. So we anyway then don't talk about what the function does at x0 to begin with. So x0 may be in the domain, might not be in the domain. Forget about that. Ask what the function is doing on the points around it. Of course, the points in the domain, because the function is defined only in the domain. So forget about the point x0. Ask all the points in the domain which are around x0 and consult them to decide what the function was trying to be at the point x0. So if it was trying to be L for each epsilon, there should exist a delta deleted neighborhood such that inside that neighborhood, all the points in the domain are epsilon loyal to this number L. Okay? Right. So when this happens, we say that limit exists. So if such an L exists, we say limit of the function exists. There is something wrong here. Yeah, that's fine. Let me come back to that comment, just 1 second. So when such an L exists, we say that the limit of the function f exists and is equal to L, limit of the function at x naught, or as a x approaches x naught, that's also how we read it. So when there is such a real number L, such that this equality indeed holds, we say that the function f has a limit as x approaches x naught, or at the point x naught, and that limit is L. And to solidify that statement, we should first of all establish as an exercise that if there is an L for which this happens and there is an M for which this happens, then L equals M. Right? So it cannot be that there are two different real numbers which give this equality. So the limit of the function, if it exists at the point x naught, and remember x naught is an accumulation point of the domain, if the limit of the function f exists, then it is unique. There is only one L, at most one L, that can satisfy this equation. There may be no such L, as we kind of saw in the motivation, but if there is one, there is only one. So this is an exercise. Let me write it. Important exercise. Just a very simple epsilon delta exercise. Okay. So I hope the motivation and the formal definition connect in your mind. And if they don't, think about it. Stay on it a little bit. And now let us look at examples. So here is our simplest example. We have a function defined on all real numbers. So this is supposed to be, there is a function from all real numbers to all real numbers, of course. And the graph of the function is drawn. At 0, the function takes the value 1. But apart from that, it behaves like the identity function. Okay. So here, the limit of the function as you approach 0, it exists and is 0. Because if you look at all the points in the deleted neighborhood of 0, they are very well agreeing that the function is trying to become 0. Okay. So this is there, and you should prove it using the epsilon delta definition. So fix an epsilon, as I've drawn an epsilon band. Can you find a delta such that in the delta deleted neighborhood, and the points in the domain, but the domain is everything, so that kind of goes away, such that in the delta deleted neighborhood, f of x minus 0 is less than epsilon? Indeed, you can. If you choose this band to have width to epsilon, then the epsilon deleted neighborhood of 0 works. Since this is the 45-degree line, if this distance is epsilon, that is epsilon, and that's it. So formally write it down, prove it formally. It's not a hard thing to prove. Okay, another example. Here again, the function is defined from reals to reals. So every point is an accumulation point of the domain. Let's talk about the limit at 0 again. And before I get there, let me mention that limit of x going to x naught of f of x in the previous example is x naught. So in general, even if you choose a point which is not the origin, of course, the delta deleted neighborhood of this point witnesses that the function is trying to become the value x naught at the point x naught. So that happens more generally here, not only for the origin. All right, what about this guy? At the origin, this function, does this have a limit? So if you make a delta deleted neighborhood and consult the points on the right side, they kind of say that the function wants to become 1. But on the left side, they witness that the function wants to become minus 1. And so this function does not have a limit at the origin. And at least the limit, if at all it is any number, it is not 1 or minus 1. But it cannot be any other number either. It cannot be this point. Here, in fact, the delta deleted neighborhood certainly does not say anything about. Delta deleted neighborhood certainly disagrees that the function wants to become that value. To prove it formally, suppose you claim that the limit is 1, say. Then you make a small epsilon band around the function. Epsilon is small enough so that this epsilon band does not contain this part. So once you draw that epsilon band, any deleted neighborhood sees that the graph of the function betrays this epsilon band. The graph of the function has points away from this epsilon band. So that's one way to prove that, or that is the way to prove that the limit cannot be 1. Similarly, the limit cannot be -1. And similarly, the limit cannot be any other thing. So this limit does not exist. Okay. We tried to do it in the Okay, lastly, this is even a more extreme example. We saw this in the motivation, that you take this function, which is this time defined only on the unit interval. Give me a second. So this function defined only on the unit interval. And as we said, it starts with 1, then becomes -1 at half, then becomes 1 at 1/4, -1 at 1/8, and it interpolates linearly in between. So its frequency of zigzagging increases as you come closer and closer to the origin. And here, if you make a deleted neighborhood around the origin, even the right side of the neighborhood, or any side of the neighborhood, doesn't say anything about the function. On the left side, there is nothing, so we can't talk about it. But on the right side, or on this deleted neighborhood intersection, the domain of the function is flailing around a bit too much. So there is no way there can be a limit. The non-existence of the limit in this example fails more miserably than it does in this example. Here, at least, the right side was saying something, that the function is trying to be 1, and the left side was saying that the function is trying to be -1. But here, it's nothing. It's just so bad. So limit does not exist at all. Limit does not exist with a little bit of anger. Okay. So there are these 3 examples, and you should formally prove everything here. You should be able to prove them, because by now we are well versed with epsilon delta, and the geometric motivation for the definition should also be clear. So there is nothing. Okay, so fine. Now for another kind of limit, so to say. So suppose f is a function from some subset of reals to reals, and again we have an accumulation point of the domain, call it x0. Then we write limit x going to x0 f of x is infinite if maybe let's see an example before I write down the formal thing. So here we have a function going from punctured real numbers. So at 3, the domain, the point 3 or the number 3 is not there in the domain. The target is obviously R, and this is the function. Takes little x to 1 upon that thing. So as you look from the right side, the function blows up this way, and from the left side, the function blows up that way. Since it is always a positive number, the function's graph will always be above the x-axis. So it's like a volcano. And again, if you look at a deleted neighborhood of 3, the function, the behavior of the graph of the function is screaming at us that I want to become larger and larger and larger. So formally, once you fix some threshold, let's say this value, there is a small enough deleted neighborhood such that within the deleted neighborhood, the function always exceeds that threshold. And that is true for any threshold that you fix. Right? So that is what is meant by this equation. And now we'll just express that in words. So we'll say this is infinite if for each threshold, for each threshold n, there is some delta greater than 0 such that in the domain of the function and in the deleted neighborhood, delta deleted neighborhood, we have that the value of the function exceeds the threshold, or is at least the threshold. Okay? So what we saw in this figure, we have just enunciated. All right. And now similarly define, here is an exercise for you, define similarly. When do we write that? Minus infinite. So you can similarly define this and come up with an example. You can just write a minus sign here and the graph of the function will flip like that. Okay, so that's another kind of limit. It seems, to me, it's a little bit disturbing that we have to put this in a separate setting, right? The previous, yeah, so when this happens, we still say the limit does not exist. That's how the convention is, at least in real analysis. We say limit exists only when you find a real number in this place, right? So we still say limit does not exist, but I would say, well, the function does find a limit, even though that limit is not a real number. So what? And indeed, in the setting of general topology, you can forego all of that. This distinction that we saw in the previous slide and this slide does not exist. Here you will put a topological space. Here will be some other topological space. Not some topological space, but something. And you can talk about the limit. And there is no distinction between infinity and that. But anyway, that is for another course. So fine. So we have this. And now let's see another kind of limit. So this time, again, we have the same setting. F is a function from a subset S of reals to reals, and assume S is not bounded above this time. Okay, so we will write. So what does this mean? It just means that for each natural number n, there is something greater than this natural number sitting inside S. That's what that means. So we write limit x going to infinity, f of x is L, where L is a real number, so maybe I should qualify that. Let L be a real number. We write that if, again, let's see an example before we finish the statement. So this function is from 0 infinite to r, and clearly this is not bounded above. Okay, and this is our function. If you graph that function, you'll get this kind of thing. Just verify. And now as you go closer and closer to infinity, or in other words, if you become larger and larger, you'll see you'll become closer and closer to the value 3. The larger you become, the closer you will be to 3. The larger you go, the closer you are to 3. Formally, once you fix a threshold, let's say I want to be epsilon close to 3, there will be something in the domain that will have the property that whenever you're larger than that, you will be epsilon close to 3. So we'll just write that down in symbols. So if for all epsilon greater than 0, there is some natural number such that whenever you're greater than that natural number and in the domain, you see that the value of the function is epsilon close to the claimed limit. Okay, and again, you can prove that if there is an L, there is only one such L that you can prove. Okay. What else do I want to say here? So yeah, so here, the non-boundedness above of the domain is kind of saying that infinity is an accumulation point. You can, that's not a formal statement, but heuristically, you should be able to connect. Okay, and now here is a small exercise that similarly define. So if the domain of the function is not bounded below, then you can talk about that thing if at all there is an L which satisfies this. The same thing. Okay, so here also we say that the limit exists. Since it is a real number, we'll say that this limit exists and is equal to L because it is a real number. And now for the fourth kind of limit, you can guess. Here, again the same setting. F is a function from S to R. S assume is not bounded above. We write limit x going to infinity, f of x equals infinity. If, again, let's look at the example. So here our function is from reals to reals. Clearly, I mean not clearly, but clearly S is not bounded above. Then as x becomes bigger and bigger, fx becomes bigger and bigger. If x is big, x square is big, and therefore, I mean, that is the idea. So here we would like to say that the limit, that this expression is infinite. So let's just write down the formal statement. If for all for all numbers m, there is a number n such that if x is in the domain and you are at least n, then the value of the function is at least m. So you've chosen a threshold. As soon as you choose a threshold, there is some number such that whenever you are greater than that number and in the domain, the value of the function is at least that threshold. We have that, and similarly you can define these three things, just the variations of that guy, and come up with examples to show that. And here in particular, I mean, here you can also see that if you go to minus infinite, this is that. And unfortunately, the convention is that still we say that the limit does not exist because it is not a real number. We still say that the limit does not exist, but that's how it is. Okay. Let me take one more example. So this is our function defined that way for x not equals to 3 because 3 is not in the domain. And then we would like to say that in this limit, 3 is not in the domain, but it is an accumulation point of the domain. Then this limit is equal to, I think, 1, not 5, 1. Why is that? Well, very simple. Because what is fx? Fx is by definition equal to that, but the numerator factorizes to give this thing, which is equal to x minus 2 for all x in the domain. And from here you should be able to easily prove using epsilon delta that this is equal to 3 minus 2, which is equal to 1. So how to compute limits? We will see this a little bit more in coming lectures, but for now you should be able to prove this at least. When fx is equal to that thing, you should be able to prove that. Okay. So, yeah, maybe since I forgot to mention, let me mention it here, that if f is a function from naturals to reals, then whatever we said about this definition, limit x going to infinity, if we write this or that, or the various other counterparts where, let me write plus minus infinity here. right? So whatever was the definition of it, this is as good as asking, or even before that, what is this? This you can think of as a sequence of real numbers. A sequence of real numbers is just a function of this sort. And you can ask if that sequence is convergent. So when we write that, it is same as the previous thing, like saying that the sequence converges to L is same as this. We defined something more general, where you could take any subset here which has no bound above. You can ask that question for any such function, but when you restrict that definition with S replaced by the natural numbers, you recover the notion of convergence, and you also recover you can ask if a sequence converges to infinity and or minus infinity, right? So that also you recover. So this generalizes the notion of the limit of a sequence. Now we have a more general object. We can ask for the limit of a function with S being any subset of the reals, and the only constraint is that the point you feed in, the point you ask the limit at, should be an accumulation point of the domain, that's all. Okay, or in the case when the domain is not bounded above, you can ask for the limit at infinity, because this is sort of an accumulation point of a non-bounded above set. All right, so I should have mentioned it previously, but I forgot. Now, one last thing, perhaps. Yeah, this is the last thing. So fix a function from subset of reals to reals, and x naught be an accumulation point of S. Then we write limsup x going to x naught f of x equals L if this limit of the supremum, that's what limsup is supposed to be, the supremum or delta deleted neighborhood. We don't care what happens at x naught. This thing is equal to L. So this is a number. I mean, it could be infinite or whatnot, but it is a meaningful thing. You take fx as x satisfies all these conditions, that is a set. Take the supremum of that set. Okay. And then you shrink the neighborhood here. If this limit is equal to L, then you declare that this is the case. So I don't want to get into too much explanation here. You should try to unravel these definitions for yourself. Okay, and whatever we defined for sequences, we defined limsup of a sequence and going to infinity an. You can recover that definition when you take S as a set which is not bounded above, write infinity here and L for L, and you can similarly come up with the correct definition which generalizes the notion of limsup of a sequence. And here is also an exercise for you, that limit x going to x naught f of x is L if and only if the liminf, so I haven't defined liminf, but that is also an exercise. You should define what this means. If and only if liminf is equal to limsup is equal to L. So just like we saw in sequences, a sequence converges if and only if its liminf and limsup match. That kind of thing. And yeah, I think that's it. Here, I do not want to give too much exposition. We will not be using this concept all that much, but it is important to be able to understand this and fill in the details for yourself by now. Try to really think about what this is saying. Maybe take an example if this is not immediately clear. But abstractly, you should be able to think about the graph of a function and what this quantity is and then what that quantity is and so on. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.